Welcome back, everybody. The topic today is a continuation of yesterday's lecture, where we looked at the introduction to copper cluster theory and the basic equations. So today we are going to continue with the discussion of the basic equations, and we are going to specialize to the derivation of doubles excitation equations, as this links pretty well with the second midterm on the pairing problem. And the pairing Hamiltonian itself is going to simplify further the type of equations which we are going to end up with. Now, most of the material here is actually from the first three sections of chapter 9 of Shavit and Bartlett, but I wanted now to switch back to the whiteboard and quickly remind you of some of the things which we did yesterday. So let's do that and switch to the whiteboard. So what we did yesterday was to introduce something which we call the exponential ansatz. Now we are going to look a little bit closer at that one, because we derived some parts of it already when we discussed Fowler's theorem in connection with the Hartree-Fock theory. So a typical example of an excitation which we can have when we look at the wave function which we derived from full configuration interaction theory, where we had a linear expansion in terms of these unknown coefficients, and where this state phi hp corresponds now to a one particle, one hole excitations, as you can see here. So this state phi hp, if we now look at the example of one particle, one hole excitation, that corresponds to this specific state which we can make here. And then when we diagonalize, we get immediately the coefficients. Now, the copper cluster approach replaces this in clusters of excitations. So, and these are coupled equations. So that's why we also call it copper cluster. And we can actually show that the general wave function can be written in terms of this exponential ansatz. Now, we saw this already when we derived Fowler's theorem, which I'm going to quickly remind you of. But what we did then, if we look at Fowler's theorem, is that we could then write exactly a state, which is now a linear combination of one particle, one hole excitations plus the ansatz for the ground state. And this ansatz for the ground state could also be your Hartree-Fock reference state or any other optimized reference state. Now, in this particular case, when we looked at the reference state or the Hartree-Fock reference state, we could then express another Slater determinant in terms of a linear combination of, because when we calculate this one, this reduces to a set of linear excitations, but we can write it in terms of this exponential ansatz. In general, however, this operator T, which we have here, is an operator which now contains one particle, one hole, two particle, two hole, three particle, three hole, and up to four particle, four hole excitations. Then some very famous approximations which we are going to encounter is one is the singles excitations, which we also discussed yesterday. And today we will focus more on what is called the doubles, or just the CCD approach, which means that we simply look at the excitations of two particle, two hole states. Then we can also include singles and doubles, and this is one of the standard approaches in copper cluster theory. And finally, we can also now add triples, or we can add more, we can add quadruples, etc. But the equations become more and more involved as we add more and more terms. One thing which is important to keep in mind, which we also demonstrated earlier, is that these type of operators which we have here, this Ti, Tj, which an example is just given by this one, they do actually commute. So that means that this is a property which we are going to use a little bit later when we are going to explain in more detail the exponential ansatz. And today the topic rotates around the discussion of the copper cluster doubles methods. But let us now go a little bit back to Fowler's theorem and remind ourselves of some of the technicalities which we had there when we could actually derive the so-called exponential ansatz, because what we have here from Fowler's theorem, from the one particle, one hole type of excitations, is that we could write the state in terms of an exponential where now T just contains one particle, one hole excitations. So let me bring back some of the lecture notes which we had from week 40. We looked partly at that yesterday, but let's now bring that back here and take a closer look at what we did in connection with the derivation of Fowler's theorem. So when we looked at Fowler's theorem, one of the things we did then was simply now to rewrite the basic state. This is just a new Slater determinant, which can now be written as an exponential as a sum over all the particle hole excitations. And this C here is the reference state. It could be a Hartree-Fock reference state, or it could be any reference states which we have chosen in terms of, let's say, a single Slater determinant. Now, one of the things which we used when we derived Fowler's theorem was simply now to write out these different terms. So what we could do, if we now single out the whole states, as you can see here, so this is a double sum of the states above the Fermi level and below the Fermi level, we could actually rewrite this in terms of a product over all the whole states. But then the sums here are then essentially limited. So we're taking the exponential here. They're simply limited by the sum over the intermediate particle states. Now, there's a very important property which we used in that derivation. And that is that if we now take and look at the square term here, that square term obviously has a different label A. So as you can see here, we have a sum over A and we have a sum over B, but I remains the same. So when we have two states with I here, then these two states, when they act on, or these annihilation operators, when they act on the reference state, they have to give 0. So that means that this operator squared is equal to 0. This is something which will be general when we now use this exponential ansatz, which means that all the terms which contain these operators T squared or to higher powers, they have to become equal to 0. So that is a property which we will use. That means that this exponential which we had up here, this form here, is then something which we will simply rewrite in terms of the expression which we have here. And Fowler's theorem allowed us to rewrite this in terms of a general creation operator, which then acts on the vacuum state. So when we extend this to more complicated clusters, what we are going to do now is simply to demonstrate this for two particle, two hole excitations. And then one can easily see that this applies to higher order of particle hole excitations. So the basic mathematics has already been discussed in connection with Fowler's theorem, but let's now just go back and look at the exponential ansatz in general for more than just a one particle, one hole excitation. So let us now go back to the whiteboard and simply look at the operator of the two particle, two hole type. So let's focus a little bit more on the exponential ansatz before we move on. And we've seen that this works now for just a one particle, one hole operator. But let us now look at a specific case where we have now written the state. So remember now that we defined this phi h of p, this specific state, is now given by a given set of particle hole excitations. So H and P can be a 0 particle, 0 hole. It can be a 1 particle, 1 hole, etc., etc. So if we now let this go over to a 2 particle, 2 hole excitation, then the state is going to be given by a pair of particle hole excitations where we have an AI, and this is multiplied with a new particle hole excitation. And this acts on a state phi 0, which is now our reference state. And this is something which we have labeled as a phi ij AB. And now you see that we can also reorder that specific operator. So this operator here can then be rewritten if we now shuffle the creation operators to the left, because we want to have this in a normal ordered form. So that means that what we get then is obviously a minus sign, AI, and B and I cannot be the same. So the Kronecker delta is obviously equal to 0. So we have an AIJ here acting on phi 0. And then we don't want to have the minus sign, so we simply interchange I and J. And then we get this form, which we have seen many, many times, for a two-body operator. So this is AJ, AI acting on phi 0. So we start with a particle-hole pair to a given power. And that gives us a new state, which means also that when we now look at this specific two-particle, two-hole excitations, we would then rewrite a general T2 operator in terms of, since this is now an operator and we are looking at anti-symmetrized matrix elements, it means that we have these amplitudes. So this is given by A, B, and IJ. We have these unknown amplitudes. So when we did this in standard FCI theory, then these amplitudes are the eigenvector coefficients. But now we are actually getting this state, which is a phi ij of AB. So if I now look at the case where I have a cluster of these operators, what we could do now, if I now just look at the particle state, so you could think of now us promoting two particles above the Fermi level, and we have a two-hole state. So suppose now that we use this operator here on a specific state. So what we are doing now, so we can write a pair cluster. So this could now be given by, and now we are inspired by what we did with the Thouless theorem. So we have this product, and we can actually, if we don't want to put these factors of 1 divided by 4, we can have A larger than B, and then we have plus, and then we have the amplitude Tij AB, and then we have this operator, which is now going to be given by, and I'm going to define this Aij AB, and this operator here is now the same as AA, AB, and then I'm having an AJ and AI. And this now acts on a two-particle state. So what I've done now, and I'm putting these I and J's to be the same so that I can actually write it out in a simpler way here. So what I would have then is a state of this type here. So this is just a two-particle state. And this is something which we would then rewrite. It's pretty easy to see that this is going to be AI of AJ acting on the true vacuum state plus a sum over all these terms, A larger than B, and then I have these amplitudes, which are undetermined, multiplied with AB dagger acting on 0. So what happens now is that we have performed the contractions between these states and these states. So if we allow each pair of fermions to interact, then we arrive at what you might call a couple cluster ansatz for the wave equation when we now look at only this type of two-particle, two-hole excitations or double excitations. So in general, what we would have then, when we now let this interact on two pairs of fermions, we have in general, we have a doubles excitation. And we can write this in terms of an A larger than B, an I larger than J. And then we have 1 plus this Tij of AB. And then we have this it should be this one. And then we have this operator which we call uppercase letter Aij and AB, which now collects the two creation operators and the two annihilation operators. And this one is acting on the reference vacuum state. Now, these operators which we have, this Aij and AB, that commutes with other such type of operators, commutes with itself. They commute with each other. So these pair clusters, which we have discussed here, this type of operators, they do actually account for most of the two fermion interaction contributions to the energies. So we would say that is a dominant contribution when we now calculate the expectation value of the energy. This applies both to fermionic systems as we see them in quantum chemistry and many solid state physics systems, and in nuclear physics as well, where we know that the pairing correlations are actually very important. Now, we can also have free particle, free hole clusters. They also play an important role. But in general, what we can do now is that the generalized copper cluster function, so the generalized, and this follows very much the same spirit as we had when we derived Fowler's theorem. So the generalized CC function, because we're generating clusters of excitations, and these would be coupled. So we would then have a psi 0 of CC, copper cluster, which is going to be given by the product of all these particle hole excitations. And I'm going to have 1 plus these unknown amplitudes, which need to be defined, multiplied with this operator, which now contains different sets of particle hole excitations. And this is acting on the reference state. Now, if we then compare with the FCI calculations, then what we had with FCI was a wave function, which now is a linear expansion in terms of the coefficients. So what we had then was something which we wrote as 1 using intermediate normalization. And then we had pH larger than 0. So that means that from one particle, one hole, etc. And then we had CH, the unknown coefficients, which we gain by diagonalizing. But this operator here, which now creates different particle hole excitations, is exactly the same. And when we did many-body perturbation theory, in particular, when we did Rayleigh-Schrödinger perturbation theory, this is something which we would then write as a sum from k equals 0 to infinity. And then we had the sum over the link diagrams only. And then we had this resolvent multiplied with the interaction to the power of k. And this is acting on phi 0. And in perturbation theory, order by order, we do actually produce the different contributions, which we then would get in copper cluster theory and in full diagonalization when we do the perturbation theory expansion to infinite order. Now, there's one thing which, as you saw also in connection with the derivation of Fowler's theorem, is that these operators, which we have here, squared, they give us 0. So when I write it like this, it's because this is acting on the vacuum state. So when we write these quantities, it's always this one acting on the vacuum state. And we know that when this is squared, that means that we have particle hole states, hole states fixed, then this is always going to give us 0. So that means that I can actually do the same thing which I did with the derivation of Fowler's theorem. I have that this operator here is something which I can now rewrite in terms of the exponential of this set of operators, TH with the unknown amplitudes multiplied with a set of particle hole excitations. So that means that when I look at the general form of this expression, I would then define an operator T, which is simply now the summation over all these particle hole excitations, where I have these unknown amplitudes, which need to be determined And in our case for copper cluster theory, this is going to be a set of coupled nonlinear equations. And that means that when I look at the ansatz for the ground state here, where we are looking at a single reference determinant, this is given by the product over all these particle hole states. We have the unknown amplitudes of P acting on phi 0, as we did with Thouless theorem. And this is the same as the exponential of this operator T, which is the sum of all distinct particle hole excitations. And this is multiplied with phi 0. Now, these different operators, let us just list them here for the sake of completeness. This is given by the sum over particle hole excitations. So this contains a TIA, and then I have an AI, AA, and AI. T2, we can write it as a sum restriction. We have A larger than B and I larger than J, or I can now simply rewrite it in terms of an anti-symmetrized operator, because these are operators. And then I would simply have this as 2 factorial squared. And then I have a sum, and now I'm summing freely over all the states, IJ and AB. So I have these amplitudes, AB, and then I have an AI, AB, and AJ, AI. And the unknown amplitudes, they now behave like an anti-symmetrized two-body element, which means that it has the same symmetries as we had for the interaction, the two-body interaction. So this is also equal to T minus T ij of BA, which is again is equal to TJI of B of A. And that's why we have this factor of 1 divided by 4 in front of it. Now, another very popular amplitude, which is used in quite many applications, in nuclear physics in particular, because we have important free body contributions. So for the T3, this is going to be given by 1 divided by 3 factorial, which is 6, and that is squared, which is 1 divided by 36. And this follows from the possible number of permutations which we can do for a 3 by 3 determinant. So 6 or 3 factorial, that's the number of permutations we can do on the single particle states for a 3 by 3 determinant. And then this would now contain some elements T, I, J, K, and then I have A, B, C. And then we start with the particle hole pairs. So we would have 3 particle hole pairs. And then we can, when we rewrite that in terms of normal ordered matrix elements or normal ordered operators, this will be given by these operators here. We would have a sum over A, B, C, and then I, J, K. And then I would have K and J and I here. So that's the an example of some of the more typical operators which we will encounter when we do this type of calculations. So if I now look at my the action of the operator on this, what it means is that my wave function is now going to be given by e to the power of t multiplied with this phi 0. So this is my copper cluster ansatz, but this has to be equal to the same wave function which we produce when we do FCI calculations. So that means that if I do an FCI calculation, this has to be equal when I now equate things. So this should then be equal to the sum over all these types of excitations which I have in the FCI calculation. And I'm just writing it like this in a simplified way. So when I now expand this term here, then I can regroup it in terms of different types of excitations of a T1 plus T2 plus T3, etc., up to T n particle n whole. This means that if I look at this term C0 and I perform the exponential development as a Taylor series, C0, which comes from my FCI case. So this is my FCI, So we want these to represent the same type of information, because copper cluster theory, if I now include all types of excitations up to n particle n hole, that should be equivalent to do a full FCI calculation. It means that when I do the C1 here, which we had before, this should be the same as a T1, so which is a one particle, one hole excitation. If I look at C2 then, and I look at the terms which I get when I do the Taylor expansion of the exponential, there will be a two particle, two hole term to the order C2. So our C2 here in FCI is simply the two particle, two hole excitation. But I also get from the exponential development, I get a T1 squared. So this represents my two particle, two hole excitations. Because I have two T1 operators, which means that I get a two particle hole pairs, and then I have a T2, which gives me a two particle, two hole excitation. Now, when we look at the operators themselves, these are going to give rise to disconnected operators, but at the end, when we bring everything together, when we take the final contraction with the final state, this can give a non-negligible contribution to the energy. So if we look at these operators in a diagrammatic way, if we now stop at the C2 level, so this is C2 here, which now contains T2 plus 1/2 times T1 squared. The T1 operator, when we write it diagrammatically, is going to look something like this. So we have a particle hole pair, which we create. If I have two such operators, so T1 squared, that is something which is going to be a disconnected diagram. So it's going to look like this. I'm not putting labels on them, but then I have a term like this one. However, since this is just an intermediate state which we create, this has to be linked with a final state. So if I have a two particle, two hole states, because this produces now, as we can see, a two particle, two hole state. So if I now link this with an operator of this type, then I can de-excite a two particle, two hole pair. So that means that I would produce something which looks like this. And this is a fully connected diagram. As long as I can now link the two particle, two hole state, which I produce as an intermediate excitation, with a two particle, two hole de-excitation. So that when I then calculate the vacuum to vacuum expectation value, or better, the reference vacuum to the reference vacuum expectation value, then I'm producing only linked contributions. So this is a typical example of an operator, and C2, on the other hand, would just be given by, so C2 here, when I do diagonalization, that actually produces these terms, and this term T2 would be nothing but a wave operator which looks like this. So this creates a two particle, two hole pair, and the only one we can match that one with in order to produce a finite contribution to the ground state expectation value is to link it with a term like this one. So we would de-excite a two particle, two hole pair. This is actually something which we will discuss a little bit more in detail next week when we look at the diagrammatic derivation of the copper cluster equations. So today we are mainly going to go through a more laborious algebraic derivation of the equations. And next week we will benefit from the diagrammatic approach, which often simplifies the derivation of different equations. Now, just for the sake of completeness, if we look at the C3 amplitude, which now contains free particle, free hole excitations in standard FCI, if I link that with copper cluster theory, that is going to contain a free particle, free hole excitation, which is a T3. But then I will also have a T1 times T2. So I have a one particle, one hole times a two particle, two hole. And that will actually then consist of two disconnected parts. It will be a two particle, two hole excitations together with a one particle, one hole excitation. And if I then want to go back to the ground state and want to de-excite it, then clearly what I need to have is a free particle, free hole de-excitation mechanism. Then what we have next here is a term which goes like 1 over 6, which comes from the Taylor expansion, and then we get a T1 cubed. And then we can continue like this with C4, which is a 4-particle for hole excitation, which will contain a T4, it will contain a T3 times a T1, it will contain a T1 to the power of 4, it will contain T2 times T2. And that way we, from the wave expansion, which we have done now with the exponential ansatz, we can then recover all the terms which we had in the linear expansion. Now, if we now look at the way we are going to find these amplitudes, because these are the unknown coefficients which we now want to determine. So one way we could proceed is simply to take the full expectation value and perform a variational calculus, which means that we would have to take the derivatives of the expectation value of the energy in terms of the different amplitudes. So one approach to find these amplitudes is actually to set up the, so let's now write this in terms of psi 0, and this is going to be Cc, and this is given by E of psi 0, Cc. And from now on, I'm going to skip the Cc subscript, but this is going to be equal to H of E of t multiplied with phi 0. And this is obviously E, and we put a 0 here to indicate that we are targeting the ground state of Et of phi 0. And what we could do now is simply to find the minimum here by performing a variational calculation. So what we want then is simply to calculate the argument of the min here, where the argument is given by this set of amplitudes, TH, TP, and then we would simply proceed as we did with the FCI, and then we have an E of minus T of H of E of T of phi 0. And this would then be divided by the state psi 0 with psi 0 here. Now, the wave function depends on these unknown amplitudes in a nonlinear way. So this psi 0, for copper cluster theory, the ansatz, that depends on the unknown coefficients, on THP, in a nonlinear way through the exponential ansatz. And if I then want to calculate the variational derivative, so that means that what I would do then is to actually calculate and optimize the energy, that would actually lead to an intractable set of nonlinear equations. So that means that optimizing this E min as function of which means that we take the functional derivative of E min with respect as function of these quantities THP. If we do this, that leads to an almost intractable set of nonlinear equations. Leads to an almost intractable set of nonlinear equations. So the standard recipe for finding these terms is actually to use what is called a projected copper cluster approach. And this is simply just called the copper cluster approach. So if we now look at the projected approach, which is the standard one used in copper cluster theory, and we normally just call this the copper cluster approach. This means that if we now think of all the amplitudes we have, this goes actually back to this set of equations which we derived yesterday, where we projected out from the left-hand side all the Slater determinants. So we looked at the Hamiltonian matrix, and then we took row by row, and each row represented then the projection of a given state on the Hamiltonian problem. So the problem which we have is obviously this one. This is where we start. And this is going to give us an E0 of E of t of psi 0. Now, when we built the Hamiltonian matrix, what we did then was to set up, and in our case, we have n single particle states and n particles. This is then the number of Slater determinants which we can make, which then also corresponds to the number of amplitudes. So we would then set up the amplitude equations. This is a total number, the total number of actually configurations which we can make. So we would set up these amplitude equations to find the energy, and that gave us the Hamiltonian matrix to find the energy, and the amplitudes. By what we called left projecting. So we acted from the left with a given set of Slater determinants. And then by left projecting by each determinant. By each determinant here. Now, the first row was actually the phi 0 row, and we have assumed in this course that the ground state is non-degenerate. So then we could simply act with phi 0, and then we had h of et of phi 0. And this gives us then, when we do the calculations here, because we also have, if we now look at the state which we had, et phi 0 on the right-hand side, this is the same as psi 0. So when I multiply with phi 0 and psi 0, that is the same as 1 because we have used intermediate normalization. So this gives us just E0. Now, the next thing which we need to think of, so this is one of the equations, and what we did yesterday was to rewrite that one in terms of the correlation energy. Now, what we want to do next is actually to take the different rows, and in each row, we would multiply with a particle-hole Slater determinant. And keep in mind again that we have a huge number of these. So this is the same as h of t and phi 0. And this is nothing but E, and then we have the projection here of P of h, and then I have Et multiplied with phi 0. So that was the projection which we did on that specific row. And in one of the cases, we would have a phi of Ai of h of Et and phi 0. And that will be given by E, this is E0 of phi of Ia. And then we have Et of phi 0. And then we could continue like that with the 2-particle 2-hole excitations, 3-particle 3-hole excitations, etc., etc. Now, the thing now is that for a truncated cluster operator, so for a truncated cluster operator, that is, we don't include all the Slater determinants which we can make. For example, if we now have a T of n, which is smaller than T, so a typical example of cluster operators which we deal with often is a T1 plus a T2. Now, in that case, we know that if I operate with this operator here, I get the E of T of n of phi 0. And this is no longer an eigenstate, a true eigenstate of the system. So this is actually going to be different from an eigenstate multiplied with T of n with phi 0. So it means that for truncated cluster operator, the full Schrödinger equation is not satisfied. It means that the states which we get will also be non-variational. and which is something which we will see a little bit later, which also means that the energy, when we are performing this type of iterations, can converge from below or from above the exact value. So if we now look at the cluster operator, which includes, let's say, only T1 and T2, what we would have then, so for say T is equal to T1 plus T2 only, then what we get now is a set of equation where we have a phi 0 of H of E of T, and then after the break, we are going to elaborate these equations. So this is one equation which we would get. And then the next equation is a phi A with the H of E of T of phi 0, and this will be equal to E0 multiplied with phi IA of E of T of phi 0. And then finally, so this is the first equation, this is the second one, and these are the basic equations which we're going to solve after the break. So, and then we have a third equation, which we then want to satisfy. So we would have a left projection with a two-particle, two-hole state, and we have E of ET, and then we're going to have a phi 0, and this is going to be equal to E0 and phi ij AB, and then we have ET of phi 0. And we see clearly that in order for this one to match the state to the left, here we would need this one to produce a two-particle, two-hole excitation. That's the only possibility. Because if I Taylor expand this one, the first one is a T1 plus T2, but then I get a T1 squared, and then I can have a T2 as well, which means that at that type of level, I would actually need higher order contributions here, where I get, in a Taylor expansion, I get a T2 or a T1 squared, for instance. So the errors which we get in the amplitude is actually, if we truncate this expansion at this set of equations, we don't include a phi I, j, k, a, b, c, etc. Then the error which we do get in the amplitudes is simply due to the missing interactions with the excitations which are absent in the operator T of n here. And that clearly also leads to an approximation to Schrödinger's equation. However, this approximation, since two-particle, two-hole excitations are so important, is actually going to be a pretty good approximation. Okay, so we have now the equations, and if we truncate at the level of singles and doubles, we have three equations which we need to solve. Now, these equations can actually be rewritten if we now look at these equations in a slightly different way. So let us remind ourselves of the fact that we are using a Hamiltonian, which is normal ordered with respect to a given vacuum state. So that means that we have a reference energy. We have this one-body operator, which contains H0 plus the Hartree-Fock potential, plus the plain two-body term. Now, what we are going to do now, if we look at the equations, we had an E of T of phi 0, and this is equal to E0 of E of T with phi 0. If I simply multiply these equations with E minus T and E minus T here, then I'm going to define a new Hamiltonian. And this means also, if you now look at the way we have rewritten Hamiltonian, if I subtract E0 ref from the left-hand side, then I get E0 minus E0 ref, which is the same as a correlation energy. And then if I recall that I call this for H of n, so the second part here is something which we call H of n. And then we have a correlation energy, which is given by E0 minus E0 ref. Now this, if I now subtract E0 ref, what I get then is a similarity transformation of h of n of e of t phi 0. So we call this a similarity transformed Hamiltonian. Now, in order for this to be unitary, this transformation, then I have to require that t is anti-Hermitian. That's the only way I can make this a unitary transformation. In general, t, the way we are setting it up, does not represent a unitary transformation. Also, it does not give us the exact Schrödinger equation, and the equations which we will end up with do not obey the variational principle. However, it's going to give us some practical equations which will allow us to set up a recipe for finding these unknown amplitudes, with obviously the constraint that the theory is not variational any longer. Now, if I then look at this equation here, then I can obviously now perform the projection again, because this equation here is equal to delta E multiplied with phi 0. Now, if I perform now the projection, so I would then have an equation here with phi 0, which I multiply from the left, and that clearly gives us delta E 0. And then I do the same with the one particle, one hole excitations and two particle, two hole excitations. So what we get then when we do the projection trick again is that we have a equation with a similarity transformed Hamiltonian of h of n of e of t multiplied with phi 0. And this is equal to simply the correlation energy. And yesterday we calculated what this correlation energy looks like if we only had a two-body interaction. And then we get the other equations. So with all the sets of one particle, one hole Slater determinants, we are going to have a new equation here, which now obviously simplifies because we are multiplying with E0 times phi 0, and that is obviously equal to 0. So that becomes equal to 0. If you can see that immediately if you go back here, because if we now look at the equation for, let's say, the one particle, one hole type of Slater determinants, what we had then, since we multiply with E of minus t, then we are simply left with phi 0, and phi 0 multiplied with the one particle, one hole excitation has to be equal to 0. So that means that we get a slightly simpler equation in terms of this similarity transformed Hamiltonian. And then we have the truncation at the level of two particle, two hole excitations. So again, we have this similarity transformed Hamiltonian, and then we have a phi 0 here, and that is equal to 0. And now we can obviously make approximations, and we can discuss whether we want to truncate t to a given order here. Now, when we are setting up the equations here, there is something which is important to keep in mind, and that is that this similarity transformed equation here contains now terms which do not commute with each other. So the term which we have here, the one body part has a potential energy which does not commute with V of n. So when I'm now calculating the expansion, if I perform a Taylor expansion of this term here, I'm going to use something which is called the Baker-Campbell-Hausdorff expansion for non-commuting operators in exponentials. And in that specific case, what we are going to get then is the following. So this E, so this is called the Baker-Campbell-Hausdorff expansion. And this is the complication which we get when we now want to use this exponential ansatz. So this similarity transformed Hamiltonian, which we have E of minus t of h of n of E of t, this is something which we can now rewrite as a term of nested, as a set of nested commutators. So we're going to get a commutator of h of n with t, and then we're going to have higher and higher commutators here. So we will get a term 1/2, and then I have the commutator between h of n and the operator t, And T now can take a very complicated form, which if we include octo triples, we are going to get pretty many terms. Normally we stop at doubles, and we have a T here, and we have higher order terms where we have pre-nested commutators, etc., etc. So this is called the Baker-Campbell-Hausdorff expansion. Now, there's an interesting result here. If we have a commutator of two operators, and their combined rank is given by the rank of operator A times B, then when I perform a commutation or set up a commutator, that reduces the rank by a factor of 2. And you can see that immediately from this one. So with a commutator, like this A and B, the result which we end up with has a rank which is less than the operator A and B. A times B has a rank which is one less, has a rank one less than the operator, the combined operator A times B. So that reduces the rank of A and B by a factor of a half. And you can see that immediately if you now look at a contribution from H of n, where we look at the H of n with T1. And this is something which we would set up. So if we look at this term with F of n and a T1 term. So let's look at that one. So a T1 term has simply an A and AI here. And this term here would then have some matrix elements, and then it has an AP dagger times an AQ here. If I now compute the, or rewrite this equation here, this will give us, when I set this in, I'm going to have an AP dagger, and I'm going to have a delta QA minus an AA dagger, AQ, so I'm just ordering the operators now so that I can cancel a specific term, minus, so this first one would be Fn times T1, and then I have a new term here, which is just T1 times Fn, and now I'm reordering them. So this will contain a term which is given by a, let me just do that one, minus, and then I have an AA, and then I'm performing one of the contractions here, minus AP of AI of AQ. So I'm just writing out the commutator. And now I see that if I look at the first term here, that is going to give me a delta Q of A, of AP dagger, of AI. And then I'm going to get an additional term, which is a delta P of I, of an AA dagger, of an AQ. But then I can reorganize these terms here and the last term here so that they actually cancel each other exactly. So what you see now is that the combined rank of these two operators, A and B, is actually given by a two-particle, two-hole excitation, but this has now been reduced to just a one-particle, one-hole excitation. So this is going to be one of the kind of simplifications which will allow us to truncate this series expansion, which you see here. Now, if you think of the Hamiltonian which we have, the Hamiltonian now is at the most of rank 2. So if you look at the two-body Hamiltonian which we have, the term which has the most complicated rank is the one which is proportional now with an AP dagger, AQ dagger, AS, and AR. So if we group this in terms of one creation and one annihilation operator, and we think of that as an object of rank 1, like the Fn operator, which we had here. So this would be rank 1 in terms of particle-hole pairs or creation and annihilation pairs. And then this operator here is also rank 1. This becomes rank 2 because I have 2 pairs of particle-hole excitations, or if we want to state it differently and not relate to particle-hole excitations, we can think of this as just pairs of creation and annihilation operators. So when we perform these operations here, we normally reduce the rank. If we now look at the Hamiltonian itself, this is something which can be thought of as a rank 2 Hamiltonian. And since the Hamiltonian is a rank 2 operators, then if we have 4 successive removes, if we look at these operators, which we would have, this nested operator, which we would have here, the next one would contain 4 nested commutators. And with 4 nested commutators, what we can do then is actually at most to have a T1 here. And each one of these operations would remove one of the operators. And at the end then, if I were to go to 5 nested commutators, and I want to calculate a vacuum-to-vacuum expectation value, then that vacuum-to-vacuum expectation value would be exactly equal to 0. So what we get then is that this expansion here terminates at 4 nested commutators if I have a 2-body interaction. So that means that when I now set up the contribution to the energy, what I'm going to get then, due to the specific properties of the commutators and the operators which I have, it means that the energy, this delta E, which I'm having here, is now going to be given by a phi 0 of h of n, and then phi 0. And then I have my nested commutators. So I have a phi 0 of commutator of hn. So these have to be evaluated depending on the approximation of t. And this is what makes many of these more approximative many-body methods sometimes a little bit more complicated than other many-body methods like Monte Carlo calculations. So we continue like this. And now I'm going to be a little bit sloppy. So I skipped the phi 0 notation. And I'm going to have 2 nested commutators now. So I will have 2 nested, and then I have an h of n of t, and then commutator with t here. And then I have my phi 0 state. And then it terminates actually at this order 4 with 4 nested commutators. And I'm simply just going to indicate that I have 3 nested commutators like this. And then finally, I have 1 divided by 4 factorial, and I have the 4 nested commutators. And then the only possibility of getting something which can be non-zero is that this operator t is equal to t1, because each t1 then will reduce the rank of the operator. So at the end, every operator which we have here can be linked with one of the t1s. So let's just continue here. And this is the final expression here. So since H is at most at 2 particle operators, it means that it can at most de-excite 2 fermions. So that means that if we look at the expectation values here, then a term like phi 0, if we now look at this multiplied with t of I, so this is our h of n here, of phi 0. This is going to be equal to 0 for I larger than 2. So since h of n is at most, in our case, a 2-body operator. This is something which will also facilitate the type of calculations which we are going to do when we now set up the diagrammatic expansion, because then we can just look at types of diagrams for both the wave operator and for the Hamiltonian, which then can be matched in order to give a non-zero contribution to the expectation value. So it's a two-body operator. Also, if we have a Hartree-Fock basis, this is important, have an HF basis. Suppose we have performed a Hartree-Fock calculation so that our reference state is a Hartree-Fock reference state. Then we know that phi 0 of Hn times T of I here multiplied with phi 0. This term here is the same as phi 0. And then I have my H of n, and then I have a one particle, one whole state where I now just picked one possible state, and we know that that one is equal to 0. So if we have, for instance, a particle whole, a Hartree-Fock basis, then there are specific terms which will vanish. Now, if we then look at ourselves limiting the calculation to the T1 level and T2 level, so if T is equal to T1 plus T2, if we look at that one, then what we have to then keep track of is simply the fact that we are going now to get contributions from delta En. So we would have a contribution from this term. But remember now that when we have a new vacuum state, Hn acting on phi 0 is equal to 0. So if we now reduce the attention to just T1 and T2, and then we also remember that this term here, phi 0, with the normal ordered part of the Hamiltonian is actually equal to 0 because we have singled out the reference energy. Then what we get is that delta E0 is simply going to be given by phi 0. And then I'm going to have the commutator of Hn. And then I have a T1 plus T2 of phi 0. And I have an additional term here, which comes from the nested commutator. And in that case, I can only have T1 because I cannot have T2 mixed in there because that would produce higher excitations. So that means that I would get a nested commutator where I at most have T1 here and T1 with phi 0. And this is where it stops for the energy. And it's easy to see that because the energy now is given here by the expectation value of Hn with some of these commutators. And we know that if we leave out T1, and this is what we are going to specialize now to, so we leave out T1. So that means that our approximation for T is going to be given by T2 only. And this is normally what is called copper cluster at the doubles level. So we have only two particle, two hole excitations. And this is normally shortened to CCD. And that's the approximation which we are going to look at now. Now, if you look at the equations for the amplitudes, there we would have similar equations. They would also truncate at the level of the fourth nested commutators. So with a two-body Hamiltonian, we get at most a quartic amplitude equation. So at most 4 nested commutators. So with this approximation now, if we do that, then what we will find is that this delta E is the same as the one which we calculated yesterday. So when we now set it in, we have an H of n, and then we have a T2 here, and then we have a phi 0. And this is going to be equal to a sum over A, B, I, J, and then I have my Tij, AB. And since I'm summing freely, it's going to have a factor of 1 divided by 4. And then I'm going to have an AB of V of Ij here. And this matrix element is anti-symmetrized. And we are going to call this for delta E CCD. That's the correlation energy, which we're going to calculate now. And we're going to try to find the expression for that. So what we have is a term here, which depends on the unknown amplitude. So if we use many-body perturbation theory, which we will do in order to start these calculations. So with the many-body perturbation theory as a guess, so our iterative guess, the first value which we're going to start with. Then we have a Tij AB of 0, which is going to be given by Ij of VAB divided by epsilon I plus epsilon J minus epsilon A minus epsilon B. So that's going to be the ansatz for the first iteration here. Now, the thing we need now, in addition to that equation, because this doesn't allow us to determine the amplitudes, we need actually an equation for the amplitudes. And this is the one which we are going to set up now. So when we now stay with the copper cluster at the T2 level, when we now set up the equations, what we need to set up now is the equation for P of H, which is a generic particle Hall excitation. And then we are going to have these nested commutators of E of T of phi 0. And this is something which we want to be equal to 0, as we discussed earlier. And algebraically, what this is going to lead us to, which leads to the following type of equations. When we are setting this up, and this is also discussed in chapter 9.3 of Shavit and Bartlett, what we are going to get then is that our excitation is a two-particle, two-hole excitation. And we have an H of n, and then we have 1 plus T2 plus 1/2 of T2 squared. So there is no, and we need to look at all these contributions here of phi 0. So when we now look at the excitations here, this is also going to be equal to a delta E of CCD multiplied with a Tij of AB. So here I'm actually keeping the equations with the full projection, where I then have the correlation energy on the right-hand side multiplied with the unknown coefficients. So if we look at the first term here, so the first term is pretty simple because that is just given by phi ij ab, and then I have hn, and we have already calculated this one. So this is simply given by the matrix element where we have now a particle Hall state, a two-particle two-hole state, which is being created by the Hamiltonian. So we end up with a matrix element of the type AB, and then we have a interaction term in Ij here. Now, if we now look at the second term contains now the possibility to excite a two-particle two-hole state. So if we take the second term in this equation, which is this one, together with that, so this is this one, and you see now the first term is nothing but this one, and the third term is going to be Hn multiplied with 2T2 squared. So if we look at the second term, that is going to be given by a phi ij ab of Hn of T2 times phi 0. So what happens then is that T2 is going to produce a two-particle two-hole excitation. So what must happen then is that when I multiply Hn with that one, I must stay with a two-particle two-hole excitation, because that's the only thing when I multiply Hn T2 with phi 0, this is going to produce a two-particle two-hole state. And we have to make sure that the quantum numbers of this two-particle two-hole state match the quantum numbers of the state which we have to the left. So if I am going to set up everything here, what we will get then are three distinct types of terms, and let's try to do that. So this term is going to look like, there's going to be a sum over k larger than L, C larger than D. Alternatively, I could just have a sum with 1 over 4. That's equivalent. And then I would sum freely. So I have my ij, ab, and then I have the term which is given by hn here. And now I'm producing, so T2 produces an intermediate two-particle two-hole state. And I'm going to label the state which it produces with the subscripts and superscripts CD and KL. And this contains now the unknown amplitude TKL CD. So what I need to do now is simply to calculate the different contributions which I get with the Hamiltonian. So there will be a term here which only contains the diagonal piece. And this diagonal piece then, when I now am setting things up, I'm going to get a term which contains phi ij of AB of H0 minus, and I have the reference energy, I'm just putting that one in here. And then I have my diagonal term of a phi ij AB. So this is A and B. And then I have to multiply this one with a Tij of AB. Then I'm going to get contributions now from the one-body part of the Hamiltonian, which is now the Hartree-Fock potential. So this is going, so I've actually singled out H0 and the U Hartree-Fock piece. And I'm coming back to what this U Hartree-Fock piece is. So then I'm getting the contributions where I have a sum over K larger than L and C larger than D. Alternatively, I can sum freely and then have a factor over 1 over 4. And then I have my phi of KL of CD. So next week, when we go to the diagrammatic expansion, we're going to see that this is going to be much easier to set up. And finally, we have a last term of K larger than L, C larger than D here. And then I have my phi ij AB of V of N. This is a two-body interaction, normal ordered with respect to the new vacuum of CD. And this is again multiplied with TKL of CD. Now, if I look at the term which we have here, this is simply going to give us the single particle energies. And that's a pretty simple term. Now, before we do that, let me just relabel these terms. So I'm going to call these terms, and I'm following Shavit and Bartlett in their textbook. I'm going to have that term. I'm going to have this term L1 here. And then I'm going to have this term L2. Then I also have a fourth order term, a square term in P2, which is this term which we have here. So we are coming back to that one a little bit later. So let's look at these terms first. And if I now go back and just simply set up this U Hartree-Fock, so this U Hartree-Fock term, normal order with respect to the vacuum, is simply given by a one-body operator over sum over P of Q. And this P is U Hartree-Fock of Q multiplied with AP dagger of AQ. And the term U Hartree-Fock, which we have here, of P and Q is nothing but this sum over K over M, states below the Fermi level of F, and then I have P of M, V of Q of M. So these are the terms which I need to evaluate. And the way we would evaluate this is simply by setting up all the contractions. So I'm just going to set up the contractions, and then I'm going to simply list the final expression which we are going to get. So if you now look at the type of contractions we get for this L0 is simply going to contain minus, and then I have epsilon I plus epsilon j minus epsilon a minus epsilon b. And then it has a plus 1/2. And then I get a sum over KL AB. And then I have a sum KL V of KL. So this is just the vacuum reference energy contribution, which we have seen many times before. And this term is then multiplied with these amplitudes Tij of AB. Now, this L1 term gets a little bit more complicated, but when I collect all terms, so let's just do that. So collecting all terms, and all terms means this L0, L1, L2, which we have defined here. It means collecting this term as well and collecting this term as well, because what comes now is simply just a boring exercise in performing all the contractions. So a typical contraction which we need to do then, let's just put that one up here. So I'm just going to set up the final result because I'm going to take the liberty of leaving this as an exercise. So this is an AJ of an AB, AA, and one of the terms which we would have to deal with, which is this Hartree-Fock contribution, would be an operator of this type. And then I have my AC dagger, my AD dagger, and then I would have my AL, and then my AK of phi 0 here. And then we would have to start looking at all the possible contractions which can be made. So if I do that, in addition, we need to set up. So this is my two-particle, two-hole state. I need to replace this one with a two-body interaction as well. And then finally, for the last term which we have, we would need to have two-particle hole excitations as well. So if I collect all these terms, I'm going to get, and you will find these listed in the final expression. We can then reshuffle the equations, and I'm going to get an epsilon ij. These are the single particle energies. So this is the same as epsilon I plus epsilon j minus epsilon a minus epsilon b multiplied with the unknown amplitude Tij AB. And this is going to be equal to AB, which is the first term we had, anti-symmetrized. And then I'm going to get a chain of more complicated terms. So I am going to get plus 1/2, and then I have a sum over CD, and then I have AB. This is a two-body matrix element, and CD multiplied with Tij CD. So the Ij indices are kept fixed, plus 1/2. And then I have a sum over KL. I have my Ij VKL. So this just follows from the type of contractions which we can make. I have a KL and AB, and I'm going to get many more terms, which I'm just going to list here. So I hope you can forgive me if I don't go through the boring derivations. Actually, you will find these derivations in sections 9.3 and 9.4 of Schmidt and Bartlett. But before I'm listing all the other terms, so this just continues on the next page. If you now take away what comes here, you see now that if I just leave out these other terms, just put them to 0, then I can actually use this ansatz which I made for the first iteration, which is this one. And you see that that follows from this final equation, because what we have now, if I just put the rest here to 0, then I simply divide by this one, which is the energy denominator. And then my amplitude is the one which I would get from many-body perturbation theory for the wave operator to first order. But let's complete this list. And this is not so exciting, so I just have to be a little bit careful here. So we have a sum over Kc. There is a new matrix element. There are many of these, Bk, of VCJ, and it's easy to actually write this or write it wrongly. So this is going to have an AC. There is a new element. So this is something which arises from the one body piece. BK, I have a V of C of I multiplied with TJK. Now for the pairing Hamiltonian, these represent contribution from the Hartree-Fock term, and they are going all to be zero. So these four terms, which sum over Kc, are all going to be terms which we can neglect. So these one-body terms actually, because I get the further terms, you can see this immediately because I have a particle state and I have a whole state, K, and I have a particle state and a whole state. And all these are by construction equal to zero if I use the pairing Hamiltonian. So the pairing Hamiltonian simplifies considerably when we are going to set up the final problem to solve. TJK of BC. So these are the one body insertions. So one body. And then finally, I'm going to get quite some two-body terms which arise from the T2 squared part. So I'm going to get plus a KLCD, and I'm going to have the matrix element KL of VCD. So this is a two-particle, two-hole excitation. And since I'm having two T2 operators, I'm going to get two T2 amplitudes. So I have CD, this is CD, and I have a TKL and CD. Sorry, this should be AB. That's one of the amplitudes. And then I have minus 1/2. And then I have the amplitudes TIJ of AC, TKL of BD. And some of these will also disappear when we look at the pairing model, plus TIJ of BD times TKL of AC. And then I have a new term, which is also minus 1/2. And then I have a TIK AB and TJL. So we are just interchanging some of the external lines here. And we are going to show in the slide, in the Jupyter notebook, you will see that this is something which we can write in a more compact way here. And then I have a final term, which is just given by TIK of AC. So when I keep iterating, I would then just insert the first iteration, and then I will keep iterating till the energy doesn't change by more than a fixed quantity. So this is a B, and that's the final term here. So with the pairing Hamiltonian, many of these terms are actually going to disappear. So let's look at this expression in a more compact form, because many of these terms which you see here, so terms like these ones, they are all given by interchanges of the external lines. So you can see here we have a CD here, and we have an AB. So in the next term, what we have done, we have kept I and J, K and L, but we have simply interchanged or swapped D with C, and then we have swapped again here D with B. So this is it's just a swapping of these different terms here. So this means that we have an operator which we can define, which simply interchanges A, B, C, D, I, J, K, and L. So let's go back to the Jupyter notebook, and then we're going to stop there. And the final expression which you saw here can actually be rewritten in a more compact way. So if we just scroll down, you will find in the notes here, you will find many more of these details which we have been discussing. But then if we now set up the final expression, So this expression can actually be written, the algebraic form here, can actually be rewritten in terms of these operators PA, B here, where we interchange A and B, we interchange I and J, and then we get the one-body operators, which will be this one, and then we have the two-body operators. And these are the expressions which we wrote down, except that now we have these interchanges of the different operators. And next week, we are going to write down and discuss the derivations of these equations in terms of a diagrammatic expansion, which is going to be much more compact and much more handy. And we are going to look at the pairing Hamiltonian again, and I will discuss a little bit more in detail the results which we would get from copper cluster theory. The thing which I'm going to do here is simply to run first the exact diagonalization. And if you look at the last values, minus 3.644, then if you continue here, there is actually a code which is taken from a textbook I wrote, which is Lecture Notes in Physics in Chapter 8. This is Lecture Notes in Physics 936. And there we also discuss the pairing Hamiltonian. You will actually, in that book, you will find a solution to the second midterm. Now, if I run my copper cluster equations, which I'm going to discuss in more details next week, you will see now that when I start iterating, my first iteration is now the many-body perturbation theory. This is actually the first iteration for the contribution to the correlation energy. And then I keep adding, so this includes also the single particle energies. And then you can see now that this result which I had, which was 3 points, so this after 59 iterations, you see that this is basically converged at the level of the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, to the 11th digit. So this is a little bit excessive, because normally you would just converge to, let's say, 10 to the minus 6, 10 to the minus 7. But you see now that this is converged to 3.6955. And if you go back to the result which you had from the full diagonalization, we're actually getting pretty close. So the full diagonalization gave us 3.3644. So we are just missing the exact value at the level of the third digit after the decimal point. So we are roughly having an error at the level of 10 to the minus 3. So next week, we are going to look at the diagrammatic way to derive these equations instead of going through all these boring particle hole contractions, etc., etc. And then with that, we are going to discuss how we can set up the T1 and T2 amplitudes, but also how we can recalculate in an efficient way the copper cluster energies with an iterative process. So the code which you will find here for copper cluster theory is just a brute force iterative process where we simply iterate over the coefficients. We start with many-body perturbation theory, and then we simply have a set of iterations which we repeat again and again. And here you can see that the number of iterations is just set to 60. And we don't have any intelligent termination test. We simply perform 60 iterations. So here we could have had a while test while number of iterations less than 60, or the energy difference is less than, let's say, 10 to the minus 6, just to give you an example.